Okay, so where did we leave off? So we finished kind of our Excel example last class. I'm going to post after class today an Excel assignment that looks very similar to this. There'll also be a part of it that's kind of what we're going to talk about today. And so that'll be due next Friday by the end of the day. Okay. We were supposed to have the exam next Friday. I'm going to push that forward one day. So it's now going to be, and I'll put an announcement on Canvas about this, but it's now going to be Monday, the 28th. Okay. So we'll do like a review kind of class that day, in-person class or on Monday. And then we'll talk more about kind of the particulars of the exam next week. But essentially, you'll have kind of like a 24-hour period after we do that, review session to complete it. I'll have it open prior to that as well. If you, I don't know, want to take it earlier and not do the review session that day, I don't know why you would choose that option. But once we kind of finish class, it'll be open for 24 hours to kind of get on and complete that. So you can do it Monday night, you can do it Tuesday prior to class. It'll be up to you. Okay. So this will be a really good template for your Excel assignment that I'll be posting today. I will also have an additional recorded lecture that I'll post. It's not going to be a full lecture, but probably finishing up what we don't get to today. And then next week, we'll have a little bit of new material throughout the week, and maybe even do a little bit of review next Friday as well. Okay. I'll also get some practice exams posted today after class. So if you're thinking about starting to study for that exam, I'll give you 2 practice exams. They'll have problems that would look very similar to what you would see on that exam. Okay. And that's kind of what we'll be, when I do the exam review, that's what we'll be doing. We'll be going through those practice exam problems. Okay. All right. Where did we leave off? Right here. Any questions for me before we kind of jump into things here today? No? No, so if you use Excel to do anything, it's just, I'm not, if it's a short answer problem, then yes. But the majority of the exam will be multiple choice. And so, I don't need your work for those. But if there is a short answer problem and you do some of the work, I even have people like put a word, like you can take a picture if you want to do it by hand. If you do it in Word, you can type it out. If you do it in Excel, you can post that, whatever medium you use, you can upload that file for a short answer. Yep. All right, so we don't really need these 2 rules today, but we are going to be using this multiplication rule that we talked about. So the fact that we can rewrite intersections as a conditional probability times whatever we're conditioning on, which remember what we're conditioning on is what's on the right-hand side of that line, okay? We'll be using this rule just kind of to substitute in some formulas to eventually get to where we want to be today. So I'm not going to kind of waste too much time here. Bayes' theorem, there's this general idea. If we know the probability of something, right, but then we receive some additional information, we then would use that information to update what the probability is, right? Because that information gives us a better idea about what the actual underlying probability might be, okay? And in the context of after we get done today, I'll maybe relate to this slide, but we'll just kind of jump into it. So the way we're going to set up these Bayes' theorem problems is we're always going to have 2 states of nature. So this is, you can think of, if you wanted to, state of nature 1 and state of nature 2, you really could think about them as events A and A complement, because they're going to be things like guilty, not guilty, HIV positive, HIV negative, pregnant, not pregnant, COVID positive, COVID negative, right? Whatever it's going to be, there is some true underlying state of nature that I can't observe, right? You're either guilty of a crime or you're not, but if I wasn't there, all I can do is look at the evidence and then try to make a decision. If you have COVID or you don't, I can't look at you, well, outside, you might have some of the symptoms, but I can't look at you and say you for sure have it, right? I don't know that true underlying state of nature. But what I can do is, sorry, before I continue. And so because these 2 states are going to be, you either have it or you don't, we can, like I said, you can think about them as A and A complement, which we know using this complement rule, the probability of an event plus the probability of its complement would equal 1, right? If I rearrange this equation a little bit. So these 2 states of nature will be exhaustive such that if I added the probability of having COVID plus the probability of not having it, that has to add up to 1, right? I'm in either one of those, I'm in one of those groups, right? So I can't observe this state of nature, but what I can observe is some test, right? I can give some test, which isn't 100% accurate, but having results from that test will allow me to get a better idea about whether or not what the true state of nature is, or whether or not you have the disease, or whether or not you're guilty or not guilty, right? And so the outcome of this test, right, you can almost think about it as we're going to have to run some experiment. The experiment is administering the test. So I'll see either E or E complement. Now, usually in the actual example, this will be like, I see the test comes back positive or negative. The jury returns a guilty or not guilty verdict, so on and so forth. All right? So I have these two states of nature. I can't directly observe them, but I can observe the results of this test. And the results of this test should give me a better idea about what the state of nature actually is. All right? So, and I said from last slide, but we can think about, all right, I can't observe this state of nature, but I want to know what's the probability that somebody maybe has COVID. Well, given that they saw a positive result on their test, I can find the probability that they actually have it. Right? This might be something I'm interested in doing, right? Because if I see a positive test result, I want to know how accurate that is. Like what's the real likelihood the person actually has that disease? Okay. So I'm going to minimize myself for a second. So if I wanted to think about this instead of COVID, I've got some better numbers for HIV. I've actually looked, I might, in that recorded video, I might do a COVID example just to kind of give you another idea, but I couldn't really find good results on like false negatives for those tests. So if I can get some better numbers there, I'll have a good example. We can actually think about that a little better. But I do have some good numbers that exist for HIV tests. And so something I might be interested in is what's the probability that a person is HIV positive given that I see a test come back positive for HIV to that person. All right, so that's eventually what we're going to find, but we're going to have to walk through how we get the formula to be able to solve this. All right? So if I want to get to this formula that I need, I'm going to start out with thinking about, I'm looking for this, right? I see a positive test result. Given that I see that positive test result, what's the probability the person actually has that disease? Whether it's COVID, HIV, whatever example we have, right? State of nature 1 and outcome of the test E. But I'll kind of, just for the sake of this, to make it easy, we see a positive test result, what's the probability that the state of nature is they have the disease? Okay. Well, I can rewrite a conditional probability as the intersection of these two events divided by the probability of what I'm conditioning on. This is stuff we talked about last class, right? Now, the problem is, I don't just know the underlying probability that, given no other information, what's the probability someone gets a positive test result? I don't know. Because it kind of, you know, I might have information about how accurate they are for people who do or don't have the disease, but like just the overall probability a test comes back positive, I might not know, I might not have that information directly. Okay. So we're going to try to break this down into a couple components. The first is, if I wanted to rewrite this numerator, this is the probability that someone gets a positive test result and they have the disease. Well, I can rewrite that as, given that they have a positive test result, what's the probability they have the disease, times the probability that they got a positive test result. Well, I can actually think about this, but in a slightly different context, right? Because it doesn't matter if I say, what's the probability of S1 and E, or what's the probability of E and S1, right? We've talked about that, that's interchangeable. So instead, I'm going to rewrite it instead of using these guys, because I usually I don't know this, right? That was part of the problem. I didn't know the denominator here. I'm not going to know it here. So because it doesn't matter if I rewrite the intersection in a different order, I also know that the intersection will be equal to this conditional probability times what I'm conditioning on. Right? Well, now it's probably a little bit easier for me to get information on what the probability that someone just has a disease is. And it's a little bit easier for me to find really what this is saying is, given they have the disease, what's the probability they get a positive result? So it's a little bit easier to get accurate information about what's like the positivity, like what's the, you know, they call them false positive, false negatives, like what's a true positive here, right? How often can it accurately identify someone that has the disease? So I probably can get this from like a drug company or something. I then say, okay, what about this guy here? I can decompose this into two different things. If I just want the probability someone gets a positive test result, that's made up of two groups. People who get a positive test result and have the disease, and people who get a positive test result but don't have the disease, right? Because these tests aren't 100% accurate. So I can break this down to those two components. And then just like I did before, I can rewrite the intersection as conditionals times what I'm conditioning on. So I'm just going to rewrite these intersections as conditional probabilities times what I'm conditioning on. All right? And like I said, you're not going to have to like go through and prove this proof, but I'm kind of walking you through to eventually, I now have something I can plug into this denominator. I have something I can plug into that numerator. If I kind of follow those colors of where I'm plugging things in at, I'm left with this equation, right? So if I wanted this conditional probability that given that I see a positive result in the test, what's the probability they actually have the disease? I can use this formula. And what this formula is really saying, so before we get like lost in these probabilities, and I'll go through some examples, this, remember, represents people that have a positive test result and have the disease. So this numerator is the first part of the denominator as well. If you kind of notice, these are the exact same thing. Now, the second part of the denominator is people who get a positive test result and don't have the disease. So it's essentially saying, if I get a positive test result, the probability somebody actually have the disease, you can almost think about this as it's the number of people who got a positive test result and have a disease out of the total number of people who got a positive test result. That's really what we're finding. And the reason why we can think about these as numbers is remember what we did last class with the Excel example? What did we first do? We found frequencies, and then simply by dividing them by the total number of observations, we could convert those to probabilities. So anytime we have probabilities, we could think about this if we had like the total number of observations or the number of observations of the population, we could really think about these as numbers as well. Okay? We're often going to have the probabilities, but we can think about them as numbers. Okay? So if we're going to use this guy right here, let's kind of put this in the context of an actual example. Have some actual states of nature and some actual outcomes for the test. Okay? Everyone got this? If we're writing anything down, any questions up to this point? I haven't started using this yet, so let me see the chat here. Okay, I'll put this over here. Good. All right, so a couple of things that we will know have to be true. The states of nature, they have to add up to 1. We already talked about this. But another important thing is going to be if I condition on the same state of nature, the conditional probabilities for the two different outcomes of the test have to add up to 1. Think about it this way. If I have a person and I know that they have COVID, and the probability that the test comes back positive, given that they have COVID, is 90%, well, given that they have COVID, what's the probability of a negative test result? Just 10%, right? Once I've conditioned on the same thing, I know that there's only 2 outcomes of this test. Those probabilities have to add up to 1. So when I condition on the same state of nature here, that's why I wrote I, because I could condition on the state of nature 1 here. The probability of the 2 outcomes of the test, the conditional probabilities, have to add up to 1. If I condition on the state of nature 2, so that's someone who is COVID negative, well, the probability they get a positive test result might only be like 10%, and the probability of the negative test result would be 90, right? But once I condition on the same state of nature, I know those conditional probabilities for the 2 different outcomes of the test have to add up to 1 as well. And I'll give you a visual of this that can help us remember in a second. If I condition on different states of nature, I have no clue what these add up to. These actually could technically add up to more than 1, right? Because this could be like, given that I have COVID, what's the probability of a positive test result? Maybe it's really high. Maybe it's like 90%. But the problem is, given that I don't have it, what's the probability of a positive? Well, if it's a high false positive rate as well, that could be like 50%. And then when I add those together, it's more than 1. Or I have no idea. It could also be less than 1. It could be any number, right? Well, it could be any number below 2, right? Because if they're both 100%, the highest we could get there is 2. But we don't really know anything if we condition on different states of nature about the sum of outcomes of different tests. Okay. So let's go to an HIV example kind of that I was kind of using, because we can get some actual data on this, right? So if I just look at, if I selected a person at random, no information about them, the probability they have HIV in the United States is about 0.6% or a probability of 0.006, okay? The probability that an HIV test records a positive result for a person that has HIV is 0.999. Now, how I'll phrase this on an exam or something would be a little bit different. So I'll write that out for you just to kind of, so I usually would say something like this. It's saying the same thing, but it makes it a little bit easier on you guys. So given that a person is HIV positive, the probability the test comes back positive is 0.999. All right, so I'll just kind of show you how I would actually say this more likely on an exam, right? And the reason why I would say it this way is because what am I really saying here? So given that someone is HIV positive, so if I'm thinking this is a conditional probability, we have that conditional line, given they're HIV positive, the probability that we see a positive test result is this 0.999. Okay? I have this written down on the next slide in just a second, but this is the information that we're given. Now, once again, I could rewrite this one as well and say, given that someone's HIV negative, the probability that the test records a positive is 0.01. I usually just like to use that terminology of given because anytime you see that word given, you should be thinking, this is a conditional probability. Okay? And then kind of finally, a question we might have is, if a test is administered at random and it comes back positive, right? So given that I see a positive test result, what's the probability the person actually has HIV or they actually are HIV positive? Okay. So this might be a question I'm interested in, right? If I see a positive test result for any disease, what's the probability I actually have that disease, right? I might be interested in that. So I can break this down, and I usually tell people, this helps a lot of people to write this down in what I call a probability tree. I think it just helps organize your information, especially if you're answering a couple different questions on it. And really just write down what you were given. So the first thing, we can kind of ignore this for a second. Let's just look at this kind of first row. All you're gonna do is you're gonna write down, okay, what are my two different states of nature? Okay. The first is I could be HIV positive. The second is I could be HIV negative. And those are my two states of nature. Now, I was directly given the probability that someone is HIV positive or has HIV, which is 0.006. So the probability someone has HIV is 0.006. Well, I know that the probability of the two different states of nature have to add up to 1. So if the probability someone has HIV is 0.006, the probability they don't have it would just be 1 minus that, or 0.994, if they have to add up to 1. But when I write this down like this, it's kind of a nice reminder that the two states of nature, these probabilities, the things that are on the same row here, have to add up to 1. Right? So it's kind of a nice visual reminder. That's why I sometimes think, tell people to write these trees down. Okay. Then I can say, okay, here's my state of nature 1 branch, and here's my state of nature 2 branch. So on this branch, I'm going to condition on the next row, and these next 2 smaller branches, condition on whatever this state of nature is. So notice I've conditioned on whether, that someone is HIV positive. So given that they're HIV positive over here on this branch, then I'm going to find the conditional probabilities for the 2 different outcomes of the test, right? So here it's, given that someone's HIV positive, what's the probability they record a positive test result? Well, we were told that was, given that someone's HIV positive, the probability the test is positive is 0.999, right? So I write that down. But I know that if I'm conditioning on the same state of nature, right, that the probability I get a positive test result is 0.999, then conditioning on that same thing, the probability that person gets a negative test result would just be whatever adds up to 1, so 1 minus this, or 0.001. Does that make sense? We're okay with that? And kind of writing it down this way, I'm also reminded that, okay, I'm conditioning on the same thing, looking for the outcome of the 2 tests. These have to add up to 1, right? Over here on this branch, on this row, these 2 guys, these 2 conditional probabilities have to add up to 1. Right? Now, if I go to the other side, now I'm going to condition on the state of nature on this side of the branch, right? So HIV negative, I'm conditioning on the same thing. Now, given that someone's HIV negative, what's the probability they see a positive test result? Well, that was where we were told that's 0.01. So I'll write that in. Well, given that someone is HIV negative, if the probability they have a positive test result is 1%, the probability they get a negative result would be 99%, or a probability of 0.99. Once again, we're on the same branch, on the same row. These 2 have to add up to 1. Okay? So I don't know, sometimes some people think this is a waste of time because they can kind of see that already, but I think for some people it helps organize and kind of get those probabilities that you weren't directly given, right? We weren't directly given these probabilities, but writing them down, we were given something that we could very easily figure out what that probability would be. Okay? Any questions on this before we keep moving? Okay. So now that I've got, I could write them down. I don't have to use a tree. I could have just written down what I was given, right? And that's fine. Okay. And then the next thing I would do is, what am I looking for? Well, remember, the question was, if the test comes back positive, so now it's given that the test comes back positive, what's the probability the person actually has HIV? So now we're looking for, given that the test comes back positive, and here where I'm writing like POS for positive, or if you write positive in there, sometimes it could just help, like, just to clarify if these things kind of are sounding similar vernacular to you. You could like write test equals positive, just to kind of remind yourself this is the result of the test, right? So sometimes the way I'll write these out, instead of just writing in the words to kind of remind myself, is something like this, right? What's the probability that the test comes back positive, or something like that? Whatever is easiest for you. I mean, when you're working on these, you're going to be the one that's actually writing in kind of whatever abbreviations represent, the events and the outcomes of the test that you're looking for. So if this is what I want, what I'm going to do is say, okay, if I try to rewrite this as just the intersection of these two divided by what I'm conditioning on. So think about the intersection of being HIV positive and getting a positive test result. I don't have that information directly up here. So if I try to write a conditional probability in a problem, and I'm like, well, I don't have the probability of the intersection of those events, right? I'm not dealing with a contingency table. I was just given some information. That's probably a pretty good indicator that we're going to have to use this guy right here. Now, what I would do is, once you've written down that conditional probability that you want to find, identify what your state of nature is and what your outcome of the test is. Once you do that, you're basically, and you'll have this on a formula sheet for the exam, you're basically just going to take this formula and then write it out in the context of your example. So our S1 was what? Being HIV positive, and E was seeing a positive test result. So everywhere where there's an S1, I would just write this formula out and replace S1 with HIV positive. And everywhere there's an E, I would replace that with test is equal to positive, or the test comes back positive. All right? So once I do that, I'll go through another example where I write it out more, right? Once I just plug in what my specific example is, I'll now have that Bayes' theorem equation written out in the context of my example, right? So all I did was, kind of think about it here as, here's my S1, here's my E. Now that I know my state of nature and my outcome of the test I'm interested in, I just go back to that Bayes' theorem equation and plug in everywhere there's an S1, I'll plug in this HIV positive. Everywhere there's an E, I plug in that the test came back positive, right? So I go back here. I'll have to clear that drawing here in a second. Oh, where was it? Oh, I didn't go back far enough, sorry. All right, if I go back here, I was just plugging everything in. So once I have that equation, it becomes really easy, right? Once I have this written out in the context of my example, now I'm just going to go look for each one of these probabilities I need from the original information I was given. So what's the probability, not, unconditional probability that someone has HIV positive? Well, I had that written down earlier, or I had it in my tree. That's just 0.006. Okay. And then what's the probability that given someone's HIV positive, what's the probability that the test comes back positive? Well, I have that up here. That's 0.999. Now notice the first part of the denominator is always going to be the same as the numerator, right? Because remember, the entire denominator really just represents like these two different types of people who got a positive test result and had the disease, and people who had a positive test result and didn't have the disease. Okay? Well, that numerator also represents the the people who had the disease and got a positive test result. So this is the exact same thing. So I'll plug in a 0.006 here, 0.999 here. What's the probability someone's HIV negative? 0.994. Right, I already had that. Now, I wasn't directly given that. We kind of got that from kind of building that probability tree, or just knowing that if I have two states of nature, the probabilities have to add up to 1. I then look at, given that someone's HIV negative, what's the probability that it comes back positive? And I have it up here as 0.01. So does it matter what variable is which? Like, could be positive? Yes. Okay. So this is where sometimes these examples get a little tricky, right? In the sense of when you're saying this out loud, someone's HIV positive, the test comes back positive. So it is important you keep clear what the two underlying states of nature are and what the two outcomes of the test are, because that does matter, right? If I had this as the test comes back positive, given that they have HIV, well, that was something I was already directly given. I don't need to use Bayes' theorem for that, right? So it is important that, S and E, they're not interchangeable, right? The ordering actually does matter. We said the order doesn't matter on intersections or unions, but it does matter on conditional probabilities, right? It's saying two completely different things. So yeah, we need to make sure that we kind of are identifying our state of nature, the thing that we like can't really observe, and then the outcome of the test, which is trying to give us a better idea about what that true state of nature is. Hopefully that answered the question. We'll hope it did. All right, so, okay. So once I plug all those values in, it's going to look something like this, right? I'm just plugging those numbers in that we talked about. So the probability that given I see a positive test result, the probability that I actually have HIV would actually be only 38%, right? Which would imply that given that I see a positive test result, what's the probability that I don't have HIV? So I'm conditioning on the same thing, right? Given that I see a positive test result, the probability I have HIV is 38%. The probability I don't have it would just be 62, right? There's only two different states of nature. So given that I'm conditioning on the same outcome of the test, if I know the probability of one of the state, conditional probability of one state of nature, I automatically know the conditional probability of the other state as well. Now, why is this so low? This actually seems, if you think about what we're saying here, this is kind of crazy. If you were to go out and take a positive test or take an HIV test and it comes back positive, there's actually only a 38% chance you have HIV or a 62% chance that you actually don't have it. Well, why is that the case? Well, let's think about what these represent. These are probabilities, but we could easily translate these into frequencies or numbers. So on top here, we had people who were getting positive test results, right, and actually have the disease. So if we think about this, right, 0.006% of people actually have the disease. So that would be roughly half a percent of like 350-ish million. So we're talking about what, about 1.75 million people there, somewhere around there, right? I mean, this isn't exact, but just to give a number to it. So there's 1.75 million people, if we gave a test to everybody in the US, who they would get a positive test result and they'd actually be HIV positive. Now, down here, this represents those same people, those 1.75 million people, but we also have a group where these are people that don't have HIV, but they're going to get a false positive, all right? So about 1%, most people don't have HIV, so this would be roughly 350 million people, but about 1% are going to get false positives. So the number of false positive people we would have would be about 3.5 million, right? So I'm thinking about now, there's 3.5 million people who will get a positive test result and don't have the disease, 1.75 million people who get a positive test result and have the disease. So we're at what? About, so what I say, 3.5 and 1.75, so for 5.25 million people. So out of those 5.25 million people that get a positive test result, only 1.75 million would actually have the disease. I don't know, if you do 1.75 divided by 5.25, you'll probably get about this value, right? I did a lot of rounding and giving you the numbers, but it'll be close to this value. Right? So the reason why that we might get this conditional probability to be so low, and it looks like, well then, geez, these tests aren't reliable. No, they are reliable, right? The false positive rate is only 1%. The correctly identifying people with is 99.9%. It's just that when you don't have a lot of people who actually have that state of nature, or in this case, have that disease, you could end up with these kind of pretty wild conditional probabilities. Because even if the false positive rate is low, if most people don't have this disease or aren't in this state of nature, you're going to end up with a higher number of people with these false positives than people who have correct positives. Right? And this is kind of a good example of that. Right? Like I said, I don't know what I think the false positive rate for a COVID test is relatively low. Like if you get a positive test result, you can be pretty guaranteed that you have it. The false positive, I think, is probably even lower than, might be lower than 1% from what I was looking at. But the problem is it's hard to get a good idea as of right now, how many people actually, what's just the general number of people out there that have kind of COVID based on the testing. So you could do a very similar example with COVID testing here. You would just have to get these guys right here, right? You would have to kind of know what the false positive, false negative rates, or the correct positive and correct negative rates are. Okay? Any questions on this before we kind of keep moving? I'll go through another example. Okay. All right, we're on time. All right, good. So, I have this other example where we can think about not just disease tests, but think about this more in the context of a courtroom. So when I say truth serum here, if you really want to, the idea behind this is that if instead of a jury, we came up with this new technology, that was this truth serum that made people confess to crimes, right? And that it was pretty good at doing so. And so I don't know how the biological mechanisms would work, but just imagine this is what we're doing, right? And if that seems too goofy for you, just imagine this truth serum as a jury. Right? So if you are actually innocent, this truth serum would make you incorrectly confess to a crime about 1% of the time, or probably 0.01. So there are issues with this, right? It'll make someone who is innocent confess to a crime about 1% of the time. And if you are guilty, it won't work, and it'll actually, the truth serum, you would still say you're innocent. You can think about this as 10% of people who are guilty could actually, this truth serum wouldn't be effective, right? They would just say that they're innocent. Okay? So if that's the case, we can think about what's the states of nature here? What are the actual underlying things that we want to know? Whether or not someone is guilty or innocent. We don't know for sure. We weren't there to observe the crime, whatever. All we have is this truth serum, this test, that will give us an outcome that should be helpful in identifying who actually is guilty and innocent. So we've got our state of nature 1. We could think about that as being guilty. State of nature 2, think about that as being innocent. We then have the outcome of the test. The truth serum either makes you say you're guilty. That could be our E. And then our E complement would be, does the truth serum make you say you're innocent? So we're just thinking about our two states of nature and outcome of the test there. We can think about that. We're also given some additional information. Of all suspects who are kind of given this truth serum, we know from past data that 5% of all suspects who are brought in are guilty. Right? So we could then say, and I should have this reads weird because there should be let's say it this way, I like this better because it's supposed to be two separate ideas. So if 5% of suspects are guilty, then assume that you see this truth serum indicate guilty, then what would the probability the suspect actually be innocent, right? So this is kind of what we're looking for. This was kind of an additional piece of information. So the first thing that you always want to start out doing is just write down what you're given. Well, this is pretty easy because it's already written down for us, right? These two conditional probabilities are already written down for us. We know that the state of nature of being guilty, the probability of being guilty, is 0.05, right? Which would mean the probability without any additional information that someone's innocent should just be what? 0.95, right? The two states of nature, the probabilities have to add up to 1. What are we looking? So we write all that down, right? What is the, what we're looking, or what are we looking for? Well, we're looking for the probability that someone is innocent, given that we see the truth serum resulted in them saying they're guilty. Right? So if we write all this down, right, these were kind of what we were given, and I'm indicating here, instead of writing out innocent and guilty, I'm kind of shorthanding using G and I. Right? That's the only kind of difference I've done there. So this is what I was given, and we weren't directly given this, but I asked you, and you kind of correctly identified the gap. The probability that someone's guilty is 5%, or 0.05 is a probability. The probability they're innocent is 0.95. What are we looking for? Well, we're saying, given that we see the truth serum make someone say they're guilty, what's the probability that they're actually innocent? That's what we're looking for. So now the next step is, we have to write this out in Bayes' theorem, right? So if I go back, I'll go back or look at my formula sheet. If I can get there. There we go. My S1 was that the person is actually innocent. My E was that the truth serum made them say they're guilty. So all I'm going to do is write out this formula using my example. Everywhere there's an S1, I'll write innocent, 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 innocent. Oh, sorry, not here. S2 would not be innocent. If S1 is innocent, what is S2? Right, so everywhere there's an S2, I write guilty. Our E was that the truth serum made them say they're guilty. So everywhere I see an E, truth serum made them say they're guilty. Truth serum made them say they're guilty. Truth serum made them say they're guilty. Once I have that all written out, I'm now going to have a formula that's pretty easy to plug numbers into. So I'll go down here. So just write that out in the context of my example. And now it's just a matter of plugging in these probabilities from the information I was given. The probability someone's innocent is 0.95. Given that someone's innocent, the probability that they say they're guilty is 0.01. Remember, the first part of the denominator is always the same as the numerator, so I'd actually have the exact same two values there, 0.95, 0.01. What's the probability someone is guilty? 0.05. Now this gets a little tricky. Given that they're guilty, what's the probability that the truth serum makes them say they're guilty? Well, I look up here, I don't have that. Right? Now, if I had written out my probability tree, that would be one of the pieces of information I would have. But even if I don't do the tree, what from here can I use to find this probability? Well, remember, if I'm conditioning on the same state of nature, I know that the conditional probability for the two different outcomes of the tests have to add up to 1, right? Given that I'm guilty, if the probability that the truth serum makes me, say I'm innocent is 10%, then given that I'm guilty, the likelihood that, or I shouldn't say these percentages. Given that I'm guilty, the probability the truth serum makes me say I'm innocent is probability of 0.1. So given that I'm guilty, what's the probability that the truth serum, I actually confess and say that I'm guilty? Just 0.9, right? And that was the idea. If we condition on the same state of nature, there's only two outcomes for the test, those conditional probabilities have to add up to 1. Now, if I had written out that probability tree, I would have had that as one of the components, right? So I write this formula out. I have everything except for this guy right here, but using this information I was given, I can derive that this is actually 0.9, right? And this should be covering this up right here. Moved over for some reason on me, okay? Any questions on that? Does that make sense? You're good with that? So really these steps are always going to be the same. Identify what information you were given, write out the probability of what you're looking for, then write out Bayes' theorem in the context of your example, because once you have the probability of what you're looking for, right, here's my S1, here's my E, just write out Bayes' theorem in the context of your example, and then start plugging things in. Occasionally, you'll have to find these missing pieces, but if you always start out building that probability tree, you'll fill in all the missing pieces. And that's another reason why I would kind of suggest doing that. Right? Kind of always trying to kind of build that tree. helps just kind of keep things organized, but it also gives you everything that you would ever need for any question I could ask you, okay? Because in that first example, the HIV one, we didn't have any missing pieces. Even if we didn't do the tree, we had everything given to us. In this one, we were missing a little bit. Okay? So if we do that, we get about 0.174, right? So even with a pretty accurate kind of truth theorem, given that someone confesses to the crime, probably they're innocent is actually would still be as high as what? 0.17, 17%, right? And that's just assuming that, you know, I guess the false kind of positives here are 1%, and then the ones we're not correctly identifying is only about 10%. Right? So even if our jury, you can think about these truth theorems as juries, right? Even if the juries are really good, they only get, you know, only make mistakes 1% of the time. If, you know, the people that are brought into court are relatively high likelihood they're innocent, then we would still end up with kind of the, you know, a lot of people in jail, right? People who confess to crimes who are actually innocent, we'd end up with a lot of people in jail who are actually innocent. Now, hopefully, these probabilities don't hold in real life, right? Once you get to a court, hopefully the probability you're actually guilty is a little higher than 5%. I kind of did this based off of suspects. If we were like to, you know, just kind of put every single person who was even a suspect in court. But we could think, like I said, we could think about this truth theorem in terms of a jury as well. So I want to point something out here. If we had the exact same sort of setup, right? Now what am I looking for? Well, now I say, okay, if the truth theorem indicates guilty, so I'm thinking about writing this down, given this truth theorem makes someone say they're guilty, what's the probability they actually are guilty, right? That's what I'm looking for here. So given that the truth theorem makes them say they're guilty, what's the probability they actually are guilty? Well, I could go through, whoops, I want to go back one more, there we go. And just rewrite this out in the context of my example, like go through and do all the work again. But notice, what did I find before? I found that given the truth theorem, excuse me, given that the truth theorem made someone say they're guilty, the probability they were innocent is 0.174. So given that the truth theorem makes someone say they're guilty, what's the probability they actually are guilty? Well, once again, I'm conditioning on the same thing, right? I'm conditioning on the same outcome of the test, and so I'm either actually innocent or I'm actually guilty. So if this probability is 0.174, when I was finding that given the truth theorem makes someone say they're guilty, what's the probability they actually are guilty? That should just be 1 minus 0.174. I could go through and do the entire, you know, go through the whole thing, write out Bayes' theorem in the context of that example. I could do it and I would get the same value, but knowing what we had before, I could actually simply find this by, you know, 1 minus 0.174. Does that make sense? Any questions on that? But if you wanted to, for some extra practice, I put this in, you know, to find that probability, and I had it written down here earlier, you could actually just go through, redo all these steps. It's just now what you're looking for is the probability that they're guilty, given the truth theorem made them say they're guilty. All right, so if you want some additional practice, you could try to like work through that example, and hopefully once you work it out, you'll end up with that 0.826, which, oops, I'm trying to go back, right, which would just be 1 minus 0.174 as well. So either way, you know, should get you to the correct answer there. Okay? Any questions on that? All right. I'm not going to waste too much time on this, but like we could think about this as a jury as well, right? So given that someone's guilty, what's the probability they actually are innocent? I kind of put a little OJ slide in there. Given that someone's innocent, what's the probability the jury actually finds them guilty? If you haven't seen Making a Murderer, you should definitely watch that. I feel like this is like old news at this point. But, you know, these are like interesting things. And, you know, one thing that we could start to do is, well, given that someone was actually innocent, like if we write this out in terms of Bayes' theorem, right? Given that someone is found guilty, what's the probability they're actually incorrectly in jail, right? That they actually are innocent. Well, if we write this out in terms of Bayes' theorem, these conditional probabilities where given that someone's innocent, what's the probability the jury finds them guilty? We're starting to get some data and information on these with things like the Innocence Project, because that's starting to give us an idea about past cases where someone actually was innocent, but they were found guilty by a jury. Or the introduction of DNA started to allow us to realize, whoa, all these people were innocent and were found, guilty by a jury, or vice versa. These people were found innocent years down the road. Once we have DNA, we find out they were actually guilty. So we can actually kind of start to get some ideas of what these probabilities are if we were to go out and kind of probably sift through some of the, I'm sure people have done like studies where they've collected how many of these cases have been kind of overturned, looking back, what were the, court cases where they found someone guilty even though they weren't, and vice versa. And we can actually start to put those values in here and figure out what % of people actually in jail right now that a jury found guilty are actually innocent, right? So this Bayes theorem has some like really, useful real world application. It's sometimes hard to get the underlying conditional probabilities, but if we have them, we can start to find some pretty useful stuff, okay? So what I'm gonna do in that additional kind of video is probably walk through this general information about discrete random variables and kind of walk through how you find a mean, how you find a variance. It's very similar to what we were doing with weighted means and weighted variances, which is why I'm kind of comfortable making it a separate short little video that you guys can watch. If you don't watch it prior to Monday, you'll still be fine once you get to Monday's classes with what we're talking about. It'll just kind of give you a little bit more context. So if you want to watch it after the fact, after Monday's class, that should be okay. But I'll get it kind of posted later this afternoon. So if you want to take a look at it for Monday, you can. I think I mentioned everything else. Any other questions for me before we kind of get out of here? Okay, so that's kind of second part of the Excel assignment that you'll see is, if I can get back here, is what we did today with this Bayes theorem stuff. So you can do it in Excel. You can like type in some of these numbers and like put in Bayes theorem into Excel if you want to. If you want to do it by hand, that's okay as well. So the first 3 questions are all about stuff that like we did last class in Excel. I want that work actually done in Excel. But the very last problem, I think it's, I don't know if I define it as problem 4 or 2, but it's the very last problem. It's got some questions about where you'll have to use Bayes theorem. If you want to do it by hand, you can do that, but then upload your Excel file for the first part of the assignment and then what you did by hand. Or you can just basically use Excel as a calculator for that last problem, and then you'll have to just upload one Excel file. Okay? If you have any questions on it, once I get it posted and you take a look at it, please feel free to email me. Other than that, I believe it should be group 1 will be showing up next Monday and Friday. Group 2 will be on Wednesday. Is that right? You guys are group 1, right? Yeah, you guys should be, because you should have been here twice this week, but we didn't have class Monday. So you'll actually be here Monday and Friday next week again. Group 2 will be Wednesday, and then we'll kind of alternate from there on out. All right? All right. Have a good weekend. Like I said, feel free to email if you have any questions over anything.